tension and signs. I think this is like one of the last big things that we have to talk about whenever we're doing forces, tension and signs. Okay, so I'm going to make our life easy at the start, and just like always, I'm going to make our life more complicated as we keep going. So we're going to start off easy, and then life gets, well, physicsy. So um, if you're going to like hang a sign up, then the easiest way to hang a sign up would be to just hang it by one rope. And, well, yeah, okay, but this is the easiest way. I didn't say it was the smartest way, right? So, like, if you take an object and you just hang it from a ceiling by, and let's just say that your sign weighs 5 kilograms, okay? There are forces acting on the sign, okay? How many forces do we have acting on the sign?
Gravity and tension.
We have two, and it is gravity and tension. So there is a force arrow going down, and there's also a force arrow going up. So I'm going to write mg, and then I'm going to write, I think y'all wanted to call it f of t, right? Okay, so we've got f of t and we've got mg. The tension is pulling up, and mg is pulling down. And they're balanced. So the amount of force going up is the same as the amount of force going down. The sign is not floating up in the air, like it's not going higher, and it's not like breaking the tension. So like if one of these forces overcomes the other one, if mg becomes greater than ft, then the line breaks. Okay, um, go ahead. That's a good question, and the force of tension is not a constant value if you apply an additional force to it. So, for example, if you have a another extra applied force that you're adding to it, so yeah, you can do that too. But like if you say you like pull down, so you have a rope and you pull down here as well, if the box or the sign is gonna stay put, then that means that the force of tension now is gonna have to be the force of gravity plus the applied force F of A. So the tension is gonna have to increase. Correct. Once the rope can no longer take that force, that means that the force of the applied force and gravity, or whatever you throw at it, is going to be greater than the force of tension, and the rope ends up breaking. So uh, we don't deal with, like, in reality, the rope will stretch out a little bit, but in physics, we just assume that these are lightweight, zero mass, unbreakable ropes. So basically, in physics, we say the more you pull on it, the more tension becomes, and we don't really necessarily think about what would cause it to break. But basically, you're looking at weightless steel cables, yeah. But that's just the way that it goes. And so we could actually find these numbers. I know that the mg going down is 5 kilograms times 10 meters per second, which would be 50 newtons going down. And if it's not moving, that means that the force of tension up is also 50 newtons. If you want to get special about it, you can say that the force going down is a negative 50 newtons because that's actually going in the downward direction. And if we were to sum the forces up together, we could say that the sum of the forces is equal to 0 because it's balanced. So the sum of the forces equals 0. That's 50 newtons minus 50 newtons is equal to 0. Okay, and that's a good solid foundation from where we're going here, because now we've got to talk a little bit. Now our life gets more complicated. Okay, what if, and this is an example of like if you're trying to install a sign and you're small brain. If you're a little bit bigger brain and you wanted to install a sign, what would you do? You put two ropes on it. Okay, you could do that too, and we'll get there. We'll get there. We'll get there. Let's say that we're going to have a sign and we're going to make it. Let's just take the exact same sign because the first one, if you put it in one spot, then it's probably going to droop one side or the other. But if you put two ropes there, at least it'll stay kind of balanced and it won't like droop to the left or the right. So you got 5 kilograms. And how many forces are acting on this sign? It is not just two this time. So this is a force diagram. So we're going to draw our forces out, not a free body diagram, but just a force diagram. I'm going to put mg going down. And there's a tension going up this way, and there's another tension going up this way. In this case, since they're all going in the same direction, because like if I were to draw the line of action, if this line is going to break, then this sign is going to go straight up and down, right? You're not going to break the line and then the yeah, the sign's not going to go like whoop, it just like go sideways this direction. It's not going to happen. So we're just going to say that the line of action is straight up and straight down. If all of our forces are in the same line of action, then we don't really have to worry about like any breaking up components or anything like that. And since the both of the strings are the same weight, then it's going to distribute those forces equally to each other. So if the force going downward is 50 newtons going down, according to Newton's second law, this is 50 newtons going this way, each one of these forces would have to be 25 newtons going up this way and 25 newtons going up this way. So adding an extra rope will decrease the amount of force necessary to hold it in place. And I do that. One of the things that I did is if you look in the back of the room back here, um, this metal is being held up by a pegboard, and I just took a rope and I just like moved it back and forth across the whole thing. So if I were to just use one rope, it wouldn't be enough. But I basically used the rope and I threaded it through so that it distributed the force evenly, and that rope is able to hold it up and not break. At least it hasn't yet. Whenever it does, I'm going to be in for it real good. That's my redneck solution to life. But that's okay. There's zip ties on it too. There's zip ties on the side securing it in place. Um, Zip ties make me a little bit nervous though, and zip ties aren't ropes, so I know, I know. That's so you know what? That's okay for now. All right. Oops, that's not. Hang on. Now I'm gonna do a hypothetical situation. If you try to make a sign like this is very smooth brain. So you don't want to make a sign like this. If you make a sign like this and then you put another sign underneath it like this, somebody's gonna laugh at you. But this is a hypothetical exercise. Okay, let's say that the top one is 10 kilograms, and let's say that the one underneath it is 5 kilograms. Okay, so I'm gonna ask you all a question. I'm gonna say, what is the tension in the bottom rope, and what is the tension in the top rope? Think so? Okay. So first of all, we know that there's a force pulling down here, right? And that force is mg. And we know that there's a force of tension pulling up this way. So I'm going to call that Ft1 because the second one up here is not the same, and we're going to call that one Ft2. And then this one going down here, this is also going to be an mg, but let's go ahead and call that m2g, and I'll call this m1g. We've got to, if you've got two masses or you got two ropes, you've got to get in the habit of putting subscripts in for your numbers, and obviously I missed it for the one down in the bottom. But you've got to get in the habit of labeling them and making sure that they're in the right spot. Okay, so like the easiest way to think about this is the 5 kilogram one on the bottom is the only thing that's pulling down on the first rope. So the first rope's tension will be the opposite of the weight of the 5 kilogram mass, which would be 50 newtons, and I'm okay with that. Okay, the top one has to hold, in order to work, it has to hold the 10 kilogram mass, and it has to hold the 15 or the 5 kilogram mass, which means altogether it's going to be the weight of the 10 kilogram mass plus the weight of the 5 kilogram mass, which I do believe comes out to 150, right? Okay, so we have different forces involved here. So I'm going to go ahead and I'll write those out. This one down here, this newtons is 50 newtons down. So how about negative 50? The M2G is negative 100 newtons. Okay. The force of tension going up is going to be positive 50 newtons. And the force of tension pulling up here is going to be positive 150 newtons. Okay? Does this make mathematical sense? Explain to me how it makes mathematical sense. Yeah. Okay. 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 So the forces are not yet equal. Okay, so like okay. Yeah, but yeah, you're right because you're looking at the 50 newtons between the 5 kilogram and the 10 kilogram mass, and you're like, well, that's plus 50 newtons, and then you're looking at the 10 kilogram in the ceiling, and then you're like, well, that's 150. But are those on the same system? Okay, so like a plus 50 newtons is just looking at the tension of the first rope, and the 150 newtons, in order to explain that 150 newtons, you have to include the 10 kilogram mass and the 5 kilogram mass, right? For the 50 newton one, you can ignore this top part, it doesn't matter. Yes, exactly. You could treat the 10 kilogram mass as if it is the ceiling, and it would not really change anything. Okay, so you have to keep in mind, like even if the numbers don't add up to each other, the positives and the negatives, it all depends on how you look at it in terms of the system. So in this case, it does make sense if you look at the entire system because the top part, the plus 150, is going to get balanced out by a negative 150, and if you look at just the block down below, the plus 50 is going to get canceled out by the negative 50. Okay. But if you have all of the number of forces out there, they may not necessarily balance out. That may be just because we're not looking at the entire system of the masses. Only halfway. Only halfway. Right. It's okay though. It's how we learn things. Okay, so they do this kind of trick often by putting a mass on a mass, but you've just got to think about like what tension, what the rope is actually holding, and what the rope is actually pulling up. Okay, they're not like super difficult questions to work through. You just have to keep that in mind. I know a lot of times whenever people see the two masses like that, they kind of like start freaking out, and they don't necessarily know which one to go with. And the answer is like think about gravity. Think about what's actually pulling stuff down. Okay? Now, what if we did something like this? What if we have a sign and I don't even think we need that thing on the other side. And we put it like this. And both of these ropes are going out this way, and we hang it in the middle like that. That is also small brain, right? Because it'll tilt. It'll tilt over to the left or the right. You'd have to get that thing like perfectly balanced, right? But what we're going to do instead is we're going to say that, the angle between these is going to be 60 degrees. You want to go 60? Okay. Yeah, 60, 60, 60. It would make 180 degrees, right? Okay, we can do that. So let's say that this is a 10 kilogram sine, which means that if we take a look at the forces, let's look and see what we've got here. So there's a force going down, right? Y'all want to write mg or you just want to write the number out? Either way, whatever works for you guys. Okay, so you could write m1g or you could just write 100 newtons. And I'm going to put negative since it is going down. Okay, how many other forces do I have acting on this? Okay, so I have the two tensions, the two ropes, the T1 and the T2. So I have T1 and I have T2. Are these two tensions the same? They should be. Can you prove it? Okay, we're gonna yeah, we're gonna have to use a little bit of brain juice to be able to prove it. But from a logical argument, it would make sense that if the angles are the same, that the tension should probably be the same in both. If the angles were not the same, would the tension be the same? Don't think so? If the angles are not the same, they can't be the same distance from the center. Why? What's hurting your brain there? Wait, what? Okay, let's go back to my original question. My original question my original question is if the angles are not the same, would the tension be the same? Okay, that was my original question. Okay. If the angles my That's true. Okay, because the argument was if the angles are not the same, then the length of the rope can't be the same to the center of the sign. Okay, so like if this 60 degrees on the right became 30 degrees, then you're going to have a much longer rope to be able to hold it in place. So by geometry alone, the lower angle won't have the same length of rope, right? So yeah, if they're different degrees, we're going to have be a little bit more what's the word? Analytical. We're going to have to be a little bit more skeptical about whether or not those tensions are going to be the same, because you're going to have to prove it to me if that's the case. All right, let's break these forces down. So that's what I'm going to do. We're going to try to break down T1, T2, and um, the weight. I think we actually have enough to be able to solve this problem. So we're going to try it. And I'm going to just take this arrow right here. I'm going to take the one that I'm highlighting in yellow. This guy is going to go right here. Okay, and I'm going to call that one T1. Okay, and the next thing I'm going to do is I'm going to break this down into horizontal components, and I'm going to break this down into vertical components. Red being X, green being Y. I'm sorry. If you're colorblind, I'm sorry. You're right. That's true. That's true. I'm sorry. It's red and green. You're gonna have to take my word for it. The arrows down below are separated by 60 degrees, and this is a right triangle, which means that we're going to have to break these things up. Okay, yeah, we're gonna have to. 30 degrees done? What do you mean? I don't understand. The other angle is 30 degrees, that's true. According to geometry, your geometry teachers told you guys that 60, 30, 60, 90. Oh, well, they should have told you something around those lines. But either way, you know that all the triangles have to add up to 180 degrees. Um, and I don't really have a lot of numbers right now. So how should we proceed with this? How should we proceed? I do know that the sum of T1 and T. Ooh, I know. Hang on. One more time. I know that the sum of T1 and T2 have to be what? I'm gonna disagree. The sum of T1 and T2 are actually not gonna be 100 newtons. I'm gonna disagree with that one. Change my mind. Right. So let me rephrase your sentence. I'm going to sculpt it around a little bit because it's like 85% true, but there's like an extra little 15% that kind of makes all physics teachers cry on the inside. And that's okay because we always deserve to cry. We're physics teachers. But here's the deal. The vertical components of T1 and T2 have to add up to 100 newtons. Okay? Not the whole thing, but the vertical components of T1 and T2 have to add up to 100. Okay? What I'm telling you is that y is 50. Yes. So like since they're the same, we know that y is 50, and we can go ahead and we can do that. So and that's actually really important because I know that this number right here, this is 50 newtons. Okay, but I also know analytically, if we use our sine, cosine, and tangent, that 50 newtons is also going to be equal to, how would we break that up? Is that a sine or a cosine or a? We're gonna do this, yeah. Okay, so it is sine, right? Yeah. So we're doing sine. Okay, so the sine of t1, so it's gonna be t1 sine theta is equal to 50 newtons. What's that? Yeah, y'all didn't even know how to say sigma back then. I don't know. I that was with centroids. That's a different level of trauma right there. Okay. Are we all okay with this T1 sine of 60 degrees? Okay. Well, you know what? That's actually a good thing because that means that we have everything except for T1. So we could actually solve for this and find out what the tension is. But divide both sides by sine of 60. So T1 is going to equal whatever 50 divided by the sine of 60 is. Sine 60. Okay, so notice it's a little bit more. So 57.7 newtons. I'll just go to the nearest tens place. So because you're actually trying to pull it at an angle, you have to have a greater tension to keep the vertical weight of gravity from being the same. So if it was completely vertical, then the tensions for each one would be 50 and 50. Okay? But the more you stretch it out horizontally, bingo, yeah. Because whenever we did the lab, whenever we dragged the box on the carpet, if you put it at an angle, you got a greater force. That's because not only are you trying to counteract the pull going this way, you're also trying to counteract gravity at the same time. So having an angle is going to create an extra tension in the string, okay, which is exactly what's going to happen here. But there's one more thing that I need to put out that, but I'll go ahead and I'll say this. We found T1, and since they're the same angle, we know that T1 and T2 have to be the same. So technically, we're done with this problem. T1 is 50 newtons, I'm sorry, T1 is 57.7 newtons, T2 is 57.7 newtons. The entire force of tension is 141.4 newtons to counterbalance 100 newtons of gravity. Where did the other force go? Yes. It canceled out. The other force canceled out, and that's actually worth noting, even though we are done with the problem. So this horizontal force this way, we now know what T1 is. T1 is 57.7. So let's go ahead and let's do this cosine one. The horizontal force is T1 cosine 60. So let's plug in 57.7 cosine 60, and let's see what we get. We're going to take that and we're going to put that right here. And while y'all do that, I'm going to make this nice other arrow going this way. Don't judge. Don't judge my arrows. You can do that. That's fair. That's fair. You have the right to judge the colors that I pick. Okay. This is also 60. What'd y'all get for that number? Okay, so this is positive 28.8 newtons. That means that on the other side, this is negative 28.8 newtons. So the other part of the tension is in the canceling of these two forces down below, the positive 28.8 newtons to the right and the negative 28.8 newtons to the left. They ended up canceling out. So does it go into play with the tension? Yeah, absolutely. but that horizontal force ends up canceling out completely. Okay, is that reasonable? Okay. So we've now learned that that was a fairly small brain way to hang a sign. So we're gonna get creative on the next one. Definitely gonna get creative. One more time. Oh, so like if you had the top one up here and it was going like this, that would have been a smarter brain way to do that, right? The force of tensions would be the same if the angles are the same. Yes. Let me go ahead and draw that out. We're not actually going to solve that problem, but it would end up being the exact same tension if you did it that way. Oh crap, that is a highlighter. Hang on. If we did the sign, if we did this, which would be a much smarter way, a big brain way to make a sign, and these angles were 60 degrees, you would get the exact same answer to the problem. The tension would still be 57.7 newtons this way. And this one would actually get your sign to not wobble like this way or that way, although it would wobble uh um it would have yaw, Y-A-W. It would rotate this way, yeah. Okay. So it would keep it from rolling, but it wouldn't keep it from yawing. So ideally, whenever you make signs, you want to try to keep it from going all the way. Y'all know the three? It's roll is this way, pitch is this way, and yaw is this way. Okay. Correct. Yeah, airplanes roll and pitch. Airplanes should not yaw. Exactly. Okay. But there are things that do yaw. You definitely want a drill to yaw. You don't want a drill to roll. Oh, maybe I lied to you. Hang on. Hang on, I lied to you. A drill rolls. What's one that goes sideways like that? A car can yaw, and it's not a problem, right? Yeah, one that goes like this. Huh? Well, yeah, you just turn. Yeah. If you turn right or left, technically you're yawing. I mean, right? Slowly, slowly. Yeah, right. Slowly. Yeah, but actually, a plane. Yeah, yeah. A plane turns by rolling and pitching, yeah. But it does end up changing its direction like that. So you want it to yaw very slowly, very slowly. Nice. Okay, let's do one more, and we're gonna do it this way. We're gonna hook a sign up like this. Here's gonna be the anchor point. It's gonna go like that. Oh no no no! You don't even you don't even know the half of my power. So we're gonna connect one side to the right, and then we're gonna connect. Don't judge me. Yeah. So super small brain, micro brain. So if this is the micro brain way to hang a sign, and we're gonna say that this sign is 10 kilograms, and I want to know because these two tensions are they gonna be the same? Yeah, I would. If you told me that T1 and T2 were the same in this case, I would be very skeptical that they would be the same. Yeah, that is a good point. Okay. Yeah, and that's exactly what we're gonna do. That's how we're gonna solve this problem. Okay. So let's think about it. What forces do we need an angle. Um, let's take a angle of how about 45 degrees? We'll do an angle of 45 degrees. How many forces are acting on this sign? Okay. So we've got the force of gravity going down. We've got T1 going this direction, and it's already labeled. I don't need to label it again. We've got T1 going this way. We've got T2 going this way. Any other forces? Nope, that's it. I think we're pretty good on that one, right? Okay, so I'm going to go ahead and I'm just going to show y'all how to do this like free body diagram way. If you make this a free body diagram, we can resolve the components this way. We've got f of g going down, and we've got the T1 going this way. And then you're going to draw T2, and T2 is going to be going like at an angle, 45 degrees. So let's see. All right, I'll let you pick the color. What color? How about blue? Rainbow components hurt my feelings. There we go. Okay. Blue is okay. We got red and blue. And this one's going to be broken up into components. This T2 is going to have some components that go along with it. T2. Okay. Um, Now we can go ahead and we can break up those components if you want to. If this is at 45 degrees, then this one's going to be T2 cosine 45, and this one on top is going to be T2 sine 45. That was whatever. Close enough. That says T2 sine 45. Okay, our line of action, since this is a sine, and we're going to assume that if gravity like breaks it down, it's going to fall straight down. So my line of action, the easiest way to put that is to make a set of crosshairs that goes like this. So I want to balance everything on the up and down of my line of action and the left and right of my line of action. Okay, so we're going to say two things that are 100% true and are very important for this. The sum of the forces in the y direction is 0. And we're also going to say the sum of the forces in the x direction is 0. And I know that that's the case because there's no motion. Okay, it's like whenever I asked you guys, like, is it moving? No. Is it accelerating? No. Okay, so if it's not moving and it's not accelerating, the sum of the forces is equal to 0 in both the x and the y direction. So all we have to do is we have to plug in those forces and sum them up. I think doing the vertical one is the big brain way to do this because I think we have, like, that force of gravity going down, we have a number for that. We don't have a number for the left and right stuff. So big brain mode, let's do the y direction first. So my sum of my forces in my y direction is what two forces? Or force components? Okay, so we have T2 sine 45 minus Fg, and Fg is 100 newtons, and that's equal to 0. So I can add 100 to the other side. So T2 sine 45 is equal to 100. Therefore, T2 is going to be whatever the heck 100 divided by the sine of 45 is. One 144.4. Okay, so T2 is equal to 144.4 newtons. Oh, 141. I'm sorry. 141. 141.4. There we go. Now, let's worry about the sum of the forces in the x direction. So if I add up the forces in the x direction and they equal 0, what are my two forces in the x direction? Mm-hmm. Okay. T2 cosine 45. That's the one that's going left and right. That's horizontal. That's this guy, right? Okay, and we've also got to balance it with T1. So that's plus T1 equals, technically T2 is negative. So why don't we add a negative on that side? Because it's moving to the left, right? Or it's not moving to the left, but it's got a force direction to the left. So let's go ahead and call it negative. Fortunately, we know what T2 is now, so we can actually plug in that number. So I'm going to say that um, T1 is equal to, so we're going to add both sides. T1 is equal to T2 cosine 45, and that's a number. What is that? 141.4 newtons times the cosine of 45 degrees. 99.98 newtons. Okay. Yeah, it's even crazier that I made this up. So that's 99.98 newtons to the right. So the force of tension over here is 99. You know what? Why don't we just say 100? It's 100 newtons going that way. I mean, that's close enough. How did you measure that? I mean, like, I'm just gonna go with 100. 99.98 is close enough to 100 for me that I'm gonna just say 100 newtons to the right. So we have a tension 2 of 141.4. We have a T1 of 100 newtons to the right, and that means that also your T2 cosine of 45 is going to be negative 100. So the positive 100 and the negative 100 cancel out. So if we were to actually like mess with the numbers, this would be plus 100, and this guy over here would be negative 100, and they would cancel out. On the top, let's see here. Vertically, we have minus 100 for FG, and T2 sine 45 is plus 100. And you know what? That actually makes a lot of sense because this is a 45-degree angle, which means the vertical and the horizontal component are equal to each other. So if we got 100 for one, then we're going to get 100 for the other one because the sine of 45 and the cosine of 45 is the same thing. It's crazy. Yeah, the sine of 45 and the cosine of 45 are the same thing. Okay, that's because they're complements of each other. Yeah. But I mean, it checks out. Okay, and that would be an example of if somebody were to try to small brain a sign design for you guys. I think that was actually one of the problems on the homeworks where they had a sign that was kind of like made this way, really kind of weird. Okay, do you guys have any questions so far? Okay. I don't think so. So I think at this point I'll go ahead and see what we're gonna do with the next couple of minutes. We got 10 minutes left. We'll start talking about our homework and where we're gonna go with that. Because I don't necessarily think we have enough time to do another problem. We'll quickly run out of time. Digital people, talk to you later.